title of the paper that's being released today in Nature Geoscience. And this is a little animated GIF that shows you the time sequence of these features. So on the left is a black and white image. This is Pallikier Crater, and it's all along the north-facing and west-facing, and it shows where we have what we call fully confirmed RSL. As of a couple of years ago, this needs to be updated, but it's the same general pattern. There's 3 regions. This just shows Mars and its orbit around the sun, and this is to explain a little bit about why we see these at different times in different places. So Mars is tilted on its axis about 25 degrees, very similar to Earth's tilt on its axis. So it
remain in a liquid form until we hit negative 70 degrees Celsius, and will not start boiling until it is 24 degrees Celsius.
And this is a little animated GIF that shows you the time sequence of these features. So on the left is a black and white image. This is Pallikier Crater, and it's all along the north-facing and west-facing, and this just shows Mars and its orbit around the sun, and this is to explain a little bit about why we see these. It's the title of the paper that's being released today in Nature Geoscience. Shows where we have what we call fully confirmed RSL. As of a couple of years ago, this needs to be updated, but it's the same general pattern. There's 3 regions.
The resolution of the paradox is to acknowledge that the layers represent a time when water was flowing from the crater rim towards the crater interior, and it filled up a series of stacks, and then subsequently those stacks of layers were eroded, and so we drive uphill into younger layers of rock, and those younger layers of rock record the flow of water to the south. So that's the reason that we don't believe that there was a mountain in the way at the time that these sediments were being deposited.
Okay, thanks. And the crater forming event that you referenced earlier was an asteroid hit, presumably?
That's right.
Okay, thank you.
Okay, the next question is from Irene Klotz at Discovery Channel.
Thanks, Jane. I have 2 questions. The first is probably for John. Can you give us some sense of the amount of data that's been collected to get to this assessment, just as far as number of observations and if it was all done with what instruments were kind of key to it? And then the second question is for Ashwin. You mentioned about the possibility of an ocean to explain a more humid environment. Is there any physical evidence on Mars for an ancient ocean? Thanks.
Yeah, hi, Irene. The first part, it is, as you know, we built Curiosity to have an integrated payload that would all work together. A lot of the stuff that we showed you today is based on the imaging that comes from the mass cams and the mollies and the engineering cameras. And I think in months to come, you're going to get to see more updates in terms of the chemistry and the mineralogy that we've discovered as well. So but in terms of, the geological framework does come from integrating all those observations, and in order to do that, the point that we like to make is that since the day we landed, we have drilled 5 holes and scooped 5 samples. We've recovered several dozen of chemical analyses from the ChemIn and the SAM instruments. We've gotten hundreds of APXS analyses, thousands of ChemCam analyses, and literally millions of data points about the environmental sensing. And so when you collect a data set as large as that, you never know which ones are going to turn out to be the most valuable. And for us, really, I have to tell you, this was a complete surprise. There was no way to have recognized this from orbit, and it took the mass cams imaging as we drove along. All that driving we did really paid off for science. It didn't just get us to Mount Sharp. It gave us the context to appreciate Mount Sharp.
In terms of evidence for the Northern Ocean, this is Ashwin. It's a fascinating area of research that's gone on for a few decades, all the way back from Viking data. And the bottom line is that there's no smoking gun for an ocean in the Northern Hemisphere. there is a large, low topography, giant basin that forms the northern hemisphere, and a lot of the valley networks, these channels that are cut into the highlands, tend to flow downhill towards that large basin. People have been looking for definitive things like shorelines in the geology, but unfortunately, a lot of that, of those kind of more definitive features have probably been eroded away over time. So instead, there's a lot of little bits and pieces that are being put together by those who are studying the possibility of a northern ocean, including looking at where the valley networks terminate. But I think one interesting piece that will contribute here is other than the geologic evidence, there's a way to infer an ocean from the climatology. As I was talking about, if we require precipitation at Gale Crater over a long period of time, if we have a long-standing lake for millions of years, the atmospheric humidity practically requires a standing body of water like an ocean to keep Gale from evaporating and to keep a vigorous hydrological cycle going. So we'll continue to look at that and add to that pretty intriguing question.
Okay, we're going to move on to a question from New Scientist and Lisa Grossman.
Hi there. I wanted to ask a follow-up from John about, you said that this was a total surprise, that I guess, what was the surprising thing about this? Because I remember talking about the possibility that Gale Crater could have been a lake and then Mount Sharp was deposited out of that lake, and then the rest of the crater eroded away from it. So what is new here that hadn't been suspected before, and what is the most surprising feature of it?
Yeah, hi Lisa, it's John. You're quite right. The fact that one might have intuited that there could have been a lake at present at Gale Crater is not a new idea. Indeed, that's the reason the landing site was selected. What is new is the way that we deduced its presence by using rover-based observations. And what Sanjeev talked about, really I can't underscore that enough, is the fact that we can actually see inclined strata on Mars is, to the geologists on the mission with experience in sedimentary geology, is something that we had really, that's the cutting edge for trying to understand the Earth. And basically, when oil companies collect seismic surveys across places, they are looking for inclined strata, because inclined strata is the way that you then get geometry that tells you where the rocks are that you're looking for. And so for us, when we saw the inclined strata and they were dipping towards Mount Sharp, that was really a great surprise. And it's hard, even on Earth, to arrive at flat layers like the type that I showed in my part and say, oh yeah, that's evidence for a lake, because it can be a non-unique interpretation. So finding the inclined strata was the big surprise.
Great, thank you.
Okay, next we're going to go to the BBC, John Amos. Hi, John.
Hi, Jane. A couple of my questions have been asked by others, so let me ask this: how do you test this going forward? What do you expect to see as you climb the mountain? If this hypothesis is correct, you feel as though you've nailed it. What would you expect to see as you went higher and higher and you got into some of the sediments that come from a drier time in Mars history?
Yeah, hi, John. John Grotzinger here. That's in fact the fun that we're looking forward to next, and who knows what the next couple years are going to hold for us. But what we are going to do is look for evidence that we go from layers that indicate this beautiful, very fine, almost pinstripe-like lamination that's very even, that might indicate settling from suspension. And then as we work up through the outcrops, and as the rover, over the next 500 meters to a kilometer of driving, we're going to keep our wheels on the Murray Formation and try to look for an episodicity in the water coming and going, because we do see the evidence that's coming from the textures and also now the geochemistry, which indicate the concentration of salts. And so we'd like to see if there are times when the lake freshens, if there are times when the lake becomes salty, if there's times when it evaporates completely and leaves behind aeolian sand dune deposits. And that will really begin to tell us about the climate history of Mars at a higher level of resolution.
If I can add to that, I mean, one thing we would expect is that we would see repeated patterns. So as we go further south and higher in the section, if our model is correct, we should see more evidence of lake deposits with deltas and fluvial deposits, river deposits coming across the top of them. So let's see if we have multiple cycles of these developed in the section.
But as you go higher, you would expect to see more salts, yeah?
Kind of depends on what the lake is doing. So as we go basinwards into the lake, it sort of depends on what the climate does. So again, there's not only the sedimentary systems that are behaving, that are supplying sediment from the crater rim, but also the climate may be changing through time, and that changes the chemistry of the lake waters. So you can go from fresh waters into saline waters. So there's a temporal constraint there in terms of climate, and also the physical in terms of what's happening in terms of the dynamic environments.
John, the last thing I would add, just because it is an important point, is that as the chemistry changes, its redox may also change, and maybe it goes from being more oxidizing to less oxidizing or reducing. And so as we're hoping to find a diversity of presentations of different environments that we can drill and learn about habitable environments and also the preservation of carbon.
Okay.
All right, thanks. Our next question is from Nature Magazine, Alexandra Whitsey.
Yes, hi. I just wanted to ask when you're next planning to drill.
We've just completed a really wonderful study of this first maybe 30 vertical feet of Mount Sharp at the site we call Prump Hills, where we spent a couple weeks doing a reconnaissance campaign with our remote science instruments, ChemCam and the MassCam. Went back after looking systematically at the whole outcrop and the data covered by that first pass. We then circled back and looked in detail with our contact science instruments, our arm-mounted spectrometer, and our hand lens imager. And then our goal was to then look at that combined data set of the chemistry and the textures and choose a couple key sites for drilling. And we're right at that point. And in fact, science team has just been discussing Friday and today where our first drill target will be for this Prump Hills outcrop. Actually, it'd be our second target, since the first thing we did after arriving here was drill Confidence Hills. But we'll probably drill our next target in the next few weeks.
Thanks, Ashwin. And the next question comes from Eric Hand at Science Magazine.
Hi, thanks for doing this. My question is for Ashwin about the timing and duration of this wet period on Mars. So you mentioned that you can now revise this wet period to maybe have been a little bit later in Mars's history, or that it was a little bit younger, 3.5 billion years ago. What was the previous best estimate for this wet period? And how did you revise it to 3.5 billion years? And then also a second question about the duration of this period. I think I'm hearing you saying that this wet period could have lasted on the order of millions of years, maybe even tens of millions of years. Is that just for the three wedges that you've seen so far, and could that wet period be longer if, as you drive up the mountain, you find more of these wedges and more of these cycles? Thanks.
Yeah, the timing of when Mars was wet and possibly warm and wet has been evolving a little bit. It used to be kind of a canonical idea that it was the Noachian, the earliest billion years of Mars. That's when Chrism, for example, has found and Omega have found all the evidence of clays in the surface materials. I think the more that we study Gale Crater and then also the valley networks, we're realizing that a lot of that wet period was probably more like 3.8, 3.6, 3.5 billion years ago. So when I say 3.5, it's plus or minus a few hundred million years. But it's more towards the Noachian-Hesperian boundary. And with Gale in particular, Gale Crater is thought to have formed only at about 3.8 billion years ago. And so, we figure that a lot of this action was happening pretty soon after that, but extended over a few hundred million years. The geology that we see when you just use very simple ideas of how long it might take to lay down these sediments, any one of these minor outcrops that we've shown may not have required more than hundreds or thousands of years, but the whole stack of the hundreds of meters of Murray Formation, in that simple accounting, we think may have taken millions or tens of millions of years. The part that we're not sure of is whether it was continuous or episodic, whether it was dry periods, etc., which is the same discussion that's happening in other parts of the planet too. Did you need a long-lived climate, or could short-term warm and wet periods account for what we see? And so that's what we'll continue to try to figure out.
But do you see the complete stack now, or is there the possibility that you'll see more cycles as you drive up, and that it could be even longer than 10 million years?
So the 10 million years is assuming what we see now, we continue to see as we go through the rest of the Murray Formation, but that's even still just a few first 100 meters of Mount Sharp. What's above that, we'll have to wait and see when we get up there.
Okay, we've got a couple of additional media calls, and before we do that, it seems like a good time to jump in with a question that came in via Twitter from Emily Lakdawala at the Planetary Society. And her question is, are there any plans to couple these stratigraphic studies with geochemical and mineralogical data?
Yeah, it's John. Yes, they're intimately interrelated, and the strategy that we've got now for Operation Pahrump is going to be something that will apply through the rest of the mission, and it's not something that we've done with rovers before on Mars. For the Pahrump outcrop, we have planned a series of 3 loops, and in the first loop, we do a lot of imaging and remote sensing with ChemCam, and then based on the integration of the remote sensing data is where we pick targets for contact science. And then we drive the rover to these locations and get the arm out and get detailed MOLI and APXS information. And then based on that, in the third loop, we come back and then we make a decision based on integration of all the geological, geochemical, and mineralogical information, what we're going to drill. And that's why we actually did the first drill as soon as we got there, to have a very broad brush view of what we might be dealing with mineralogically, as seen by Kemen and Sam. So it's very much integrated.
Okay, and we're going to take a couple of more questions, and then if anybody, I'll do sort of a last call. So if anyone has already asked a question and wants to come back, we'll try to get a few more in if possible, if time allows. But right now, we're going to jump over to Ken Kramer at America Space for a question. Ken?
All right, thanks for taking my question and for doing this. Can you guys estimate the depth of the lake? I'm not sure you mentioned it before, and the total buildup time for Mount Sharp. And also, if I'm understanding this correctly, the sediments that built up Mount Sharp, these have come primarily from the crater rim then. Would it ever be worth sending some type of a rover there to do an investigation to get some more data on this? Thanks.
Sanjeev, you want to jump in and take a stab at that one?
So estimating the lake depth, so actually the inclined bedding is really helpful to us, because that actually, the height of the inclined beds actually tells us the water depth at the time of formation. So actually these lakes were probably quite shallow. The inclinations have heights of several meters, a couple of meters. So what's actually happening is that you have shallow lakes, few meters, maybe deepening further to the south. We can tell this water depth from where we have the inclinations. But through time, the lake deposits get stacked up as you have multiple cycles of delta growth into a lake, deltas receding and the deltas growing out. So what you're actually building up is the lakes existing in time, maybe episodically, but existing in time for long periods, but not necessarily an extremely deep lake. So it's not necessarily Lake Baikal, hundreds of meters deep. But this is actually a hard problem. In fact, on Earth, what we do is we actually look at fossils and organisms to work out lake depths. Obviously, if we had that, it would be wonderful on Mars already. In fact, this is why actually looking at the sediments, the coarse-grained sediments, the sandstones and pebble beds, and these inclinations has been really helpful to getting a snapshot of that lake depth. John, do you want to add to that?
Yeah, I'll just say, Sanjeev, we do have a part of Earth history where we don't have all those organisms to help, and for the first 4/5 of Earth history, the way that we recognize lake deposits is almost exclusively from understanding the stratigraphic geometry of the deposits and also looking for sedimentary structures that indicate what current regimes were. So we're doing exactly the same thing on Mars as we do on the early Earth. It's rather remarkable.
Okay, we're going to take our next question from Leo Enright at Irish Television.
Thanks very much, Jane, and thanks to everyone for doing this. I'm very struck by those gorgeous thin-bedded sediments in Grotzinger 1. And I was just wondering, are these exactly the sort of sediments where you'd hope to identify preservation of organics, or am I oversimplifying things? My other thought was that this image seems to be, it's hidden valley as I understand it, so it must have been out of reach. And I'm wondering, are you satisfied that you can get to that particular epoch and do some of that geochemistry that Emily was talking about?
Yes, Leo, it's John here. Good question. That first image, actually, we saw very similar things, in fact, identical things at Hidden Valley that we were not able to work in with the rover, and so we pulled out and we went into Armagosa Valley, which is where this image is from. And that did two things for us. It told us that what we saw at Hidden Valley was not the exception because we saw it again, and that's always reassuring to see a common motif. And yes, either Grotzinger 1 or Grotzinger 2 would be the kind of rock where, from a primary concentration point of view, that would be viewed as an attractive candidate for drilling. But let me remind, I know I've been saying this for years, but the preservation thing depends on having an initial concentration of organic carbon, then that the diagenesis, the geochemistry that happens when you convert sediment to rock, is a favorable event, and then it depends on how long the rock has been lying around on the surface getting zapped with cosmic radiation. And all three of those things have to go our way for us to be able to make a discovery. So, but nevertheless, based on its physical features, this would be an attractive thing for us. For the unit Grotzinger 1, for that particular centimeter-scaled stuff, that outcrops at the tops of the valleys. And so we'd really have to scratch and claw our way up there to get to that. So we're hoping for one of two things to happen. Either our future traverse takes us uphill in a way that we might be able to intercept that with less risk to the vehicle, or that a block of it rolls down the hill where we can be confident that it's the same thing, and then we might be able to drill it that way. But we would love to have a go at some of this stuff.
Okay, I'm going to do a very last call, so if there are any more questions, press *1 right away, and we try to take a couple more. But in the meantime, we've got a question, again, from Irene Klotz at Discovery Channel.
Thanks. If Michael Meyer is still on the call, you've been kind of quiet the rest of the conference. You brought up the subject of habitability in your opening comments, and just wanted to follow up on that for a minute. And I know that this isn't really there's not really a clear answer for this, but why is it that you believe that this is evidence that Mars had the right water conditions for the time needed for life to evolve, seeing how we don't really even have that information for how life got started on Earth? Thanks.
So, yeah, I appreciate the question. This is based on the publications that came out in December and then were highlighted in the January issue of Science, which basically looked at Yellowknife Bay and the pH of the water, the low salts in the water, so it's relatively fresh water, water itself, the presence of different oxidation states, all of these things pointing to a very habitable type of environment, one in which, at least as far as we know, Earth microbes may have a perfectly happy time living there. And so in many ways, what I was speaking to is the conclusion from that January issue that at least in one point in time on Mars, from everything that we know, it was habitable. But the big question was, for how long? I mean, if you had water for a very short period of time, would it be sufficient time for any potential life to take advantage of it? At least now, with looking at the size of a lake in Gale Crater and the length of time and series that water was showing up, that implies that there may have been sufficient time for life to get going and thrive. But you make a good point. The information that we have in terms of how long does it take life to start or to originate, and how long does an environment have to be there before life can take advantage of it, these are things that we don't have a very good handle on here on Earth, much less the possibilities on another planet.
And Irene, it's John. Let me just add one bit to that that came up when Eric Hand asked his question. The rocks that we see at Pahrump are only 10 or 15 meters thick. Now that's a lot more than the 1.5 meters of rock of mudstone we had down at Yellowknife Bay. But we're hypothesizing that if this similar kind of rock extends upwards through the rest of the Murray Formation, which is on the order of 150 to 150 meters thick, and that's just the first unit of Mount Sharp. If what we see at Pahrump is applicable to the rest of the Murray Formation, and we get done testing it with the vehicle, that's when you get up to the tens of millions of years time scale. What we're looking at now is on the order probably of tens of thousands to a million years, and that's more than we had down at Yellowknife Bay. But what's out in front of us and still to be tested is where we get really to the longer duration estimates for water being present.
Thank you.
All right, thank you. And we're going to take one last question. A few minutes ago, we asked a question that was allegedly from Emily Lochtawala. It turns out that question actually came from an individual on Ustream, so thank you to that individual for that question. And now I'm going to pose the question that came in from Emily, and this is, again, via social media. So Emily's question is, how has the composition of the rocks changed from delta to the lake bed? Do you want to take a crack at that?
So we don't have enough data to know if it's significant or not, but we have been drilling the rocks as at Yellowknife Bay and then also at Kimberly. And what we noticed, the big difference so far between what we drilled there and what we found at the first hole we drilled in Pahrump was that the hematite concentration went up substantially. There's still magnetite, but there's also hematite there as well. And that was, by the way, something that was predicted from orbit, that the Murray Formation should have some component of hematite. There was also a prediction for some clay, which we saw there as well. And but we're just not going to know until we drill more holes, but that's coming up in the next month or two.
Okay, and on that note, thank you to all our speakers, Michael, Sanjeev, John, and Ashwin, and thanks to everyone who joined us this morning. There will be a replay. The telecon will be archived for 1 week. If you'd like to call 866-396-6287, that's 866-396-6287. And it will also be archived with visuals on Ustream at www.ustream.tv.
Is the title of the paper that's being released today in Nature Geoscience. And this is a little animated GIF that shows you the time sequence of these features. So on the left is a black and white image. This is Pallikier crater, and it's all along the north-facing and west-facing, and it shows where we have what we call fully confirmed RSL. As of a couple of years ago, this needs to be updated, but it's the same general pattern. There's three regions. This just shows Mars and its orbit around the sun, and this is to explain a little bit about why we see these at different times in different places. So Mars is tilted on its axis about 25 degrees, very similar to Earth's tilt on its axis. So it
remain in a liquid form until we hit negative 70 degrees Celsius, and will not start boiling until it is 24 degrees Celsius.
And this is a little animated GIF that shows you the time sequence of these features. So on the left is a black and white image. This is Pallikier crater, and it's all along the north-facing and west-facing, and this just shows Mars and its orbit around the sun, and this is to explain a little bit about why we see these. It's the title of the paper that's being released today in Nature Geoscience. Shows where we have what we call fully confirmed RSL. As of a couple of years ago, this needs to be updated, but it's the same general pattern. There's three regions.